Hi viewers, welcome back to the first lecture of the series of lectures on Introduction to Category Theory. We discussed the definition of group and that of a category in the first segment. Now, I want to explain how one can obtain a category out of a group. We have this old mathematical idea of an abstract group, and we can translate it into the language of category theory. All right. So, an important feature of a group is that we can compose any two elements of the group to obtain a new element of it. We observe the following similarities between the structure of a group and the structure of a category. On the left, you have a group. On the right, you have a category. These similarities can be seen using the definitions of the group and that of a category. On the left, we have group elements. On the right, we have morphisms. On the left, we have group multiplication, which is of course associative by definition. On the right, we have composition of morphisms that we explain when we define the category. Which is also by definition associative. The third similarity between group and category is that of a neutral element and the identity morphism in the category. On the left, we have the neutral element 1 in G. On the right, we have the distinguished morphism that we introduced in the definition of category. Distinguished morphism I, D, X associated with the object X in C0. Okay? So these are the similarities. So using the similarities, we want to view the group elements of the group as morphisms in a given category. Group multiplication between the group elements as the compositions of those morphisms, and the neutral element of the group as the identity morphism on a given object. Okay. All right. So far, so good. Okay. Now observe that for a general category, you always need to match the source and target to compose the morphisms. Meaning, if you have a diagram given by three objects using three morphisms, I mean, you have a diagram of 4 objects using 3 morphisms, you can compose G with F since target of F is the same as the source of G, which is the object Y. Okay? So this makes sense. Since the target of F is the same as the source of G, this makes sense. Alright. But how about H composed with F? Does it make sense? It does not. Because the here H composed with F won't make sense because the target of F is not the same as the source of H. Alright? Target of F is not the same as the source of H. Therefore, this does not make any sense. Does not make sense. So matching these source and targets of the corresponding morphisms is very important to compose morphisms in the setup of category, of a general category. Okay. Now, contrary to this picture, for a group, we see that we can always find the element resulting in from the multiplication of any 2 elements of the group. Meaning, if you have a group element G1 and another group element G2, you can always multiply them to get a new element. Okay? Say, called G1 dot G2. Okay? Say, if in a group one has elements like this, all these group elements are defined by the general definition of a group. What does it mean? It means that the matching of the source and the target gets relaxed in the setting of a group. Okay? And this can only be achieved if all the objects for the group is the same. Meaning that if you want to make a category out of a group, all the objects have to be the same. Using the diagram, we can draw it like this. Since we want to represent the morphisms with the group elements, the objects all have to be the same. Because G2 times G5 should make sense. The source and targets the corresponding source and targets should also match. And the only way they can be matched is to take all the objects to be the same. Alright. So we can see that in order to make the group a category, there can be only one object in this category, meaning that this new category is equipped with a single object, and the morphisms are precisely the group elements, and the composition of these morphisms is given by the group multiplication. This construction of a category out of a group has has a name called delooping of G, denoted by BG. Is called the delooping of G. Okay. So it is a category. So we constructed this category BG, or the delooping of G, starting from the group G. This is a category, BG is a category in the following way. There is a single object which we have argued a little earlier. There is a single object in this category. There is a morphism. There is a morphism for each element. For each element, G in G, which maps a single object to itself. So we denote the morphisms with the same letter, G, of the group elements. So G is a morphism of the single object to itself. Thirdly, the identity morphism, is precisely the neutral element of the group. This is how BG is a category, the delooping of G. Also, I forgot to mention another point about the composition of morphisms done by the group multiplication. Composition is given by the multiplication of G. Multiplication of G. That is, given the morphisms G and H from the single object to itself, the composition of G with H is given by G dot H. This is the group multiplication of G and H. Okay? So far so good. So now we know how to construct a category from a group called the delooping of the group. Okay? Alright. Now, if we further delve into if we further delve into the construction of this delooping of G, we see that we never used the inverse law in this construction. The inverse law, we never used the inverse law of the definition of the group into this construction. So, it is a sort of redundant property of the group in the sense that we never use it in the construction of the category. So even if we relax this property in the definition of the group, we still get a category. by delooping the group. So it motivates us to define monoid. Let me write down the definition of a monoid. A monoid is a non-empty set together with a distinguished element one in M, again called the neutral element or the unit. A binary operation called multiplication. That is, for each pair from this M cross M, we must have G dot H in M again. You should remember that there was a third notion in the definition of group called the inverse, which we have relaxed here. There are only two here, and we require this structure to satisfy the following properties. A. Unitality. For each element of the set, we must have 1 dot G equal to G dot N equal to G itself. B. The associativity, which tells you that for any three element of the set, one must have G dot H dot I is the same as G dot H dot I. Okay. There is no other requirement. The inverse law is omitted from this definition to get the definition of a monoid. So, given this structure, if we do the same construction of delooping the group on this set, we get the delooping of a monoid resulting in a new category called Bm. It is very easy to see how Bm forms a category using the same construction of the delooping of a group. Okay, there is a small comment here. Okay. For the delooping of the group, observe that each morphism is invertible, meaning that each morphism was originally represented by a group element which is invertible by the definition of the group. So each morphism in the category BG was by definition invertible. Okay? But in general, when you have a category, you don't require the morphisms to be invertible in general. Okay? So, here is the comment. A category for which every morphism is invertible has a name called groupoid. Okay? So the category BG is an example of a groupoid. Okay? Where the inverse of the morphism G is given by G inverse. So the delooping of G is indeed a groupoid. So we'll study all these terms related to category theory in fair detail in due courses. Okay. Now, I need you to introduce the notion of a representation of a group. I need you to understand the concept of the representation of a group. So let me define what it means. Let me define the group representation. Very briefly, we want a map like this, where G is the underlying group, V is a vector space, GL means general linear. So say if you have an n-dimensional vector space, GLV means the invertible matrices on that vector space, meaning that the set of all n times n matrices which admit inverses. Not all n times n matrices are invertible, as you know from the basic linear algebra. You only take the invertible n times n matrices to form the set GLV, where V is an n-dimensional vector space. Okay? So we want this map to be a homomorphism. Those who are not familiar with the concept of homomorphism should understand it as just a structure preserving map. So under this map, the group structure is not violated. Let me explain it with a simple example of two group elements, G1 and G2, multiplied with the group multiplication. When we take the map of this resulting group element under this homomorphism rho, the result is precisely a matrix appearing here, if V is finite dimensional, of course. For simplicity, let's take V to be finite dimensional. So on the left side, you have a matrix, and you want this matrix to be precisely the multiplication of two matrices, like this. This is multiplication of matrices. So on the right side, you have the multiplication of two n times n invertible matrices, which is again an invertible matrix of size n times n. On the left, you also have an n times n matrix. You want these two matrices to be the same to make it a homomorphism. So this is precisely the definition of a group representation. You want to view the group elements as matrices on certain vector space. You sometimes have difficulties of studying the group, the abstract group, so you take the structure of the group, or you embed the structure of the group in the space of the matrices and study the group there to understand it more clearly. So this is the purpose of group representation. All right, so this is briefly what it means by a group representation. Now, I want you to understand the idea of functor very roughly. I tell you what it means by a functor. Okay. So before that, I want to introduce another important category for our purpose called vect C. In general, it's vect F, where F is a ground field. Whenever you talk about a vector space, you always have a ground field over which the vector space is defined. Okay? It is precisely the field from where you pick up the scalars. Okay? So it can be, in general, anything like the field of complex number, this field of real numbers, or the field of rational numbers, or some fancy field. But for our purpose, we stick to the field of complex numbers. So for this category, the objects are the complex vector spaces. These complex vector spaces are the objects of this vect C. And what are the morphisms? The morphisms here are C-linear maps. You should know the meaning of C-linear maps from your elementary linear algebra course. Even if you don't remember, don't bother about it. I'll explain it for you. A C-linear map is a transformation from the vector space to itself, meaning that it is like a matrix, where if you choose two vectors in this vector space and act this transformation on an arbitrary vector of the form alpha v plus w, you should get alpha times av plus aw, where alpha is a complex number. So this is the definition of a C-linear map. So these C-linear maps, or matrices for the finite dimensional vector spaces, are precisely the morphisms of this category, and the objects are the complex vector spaces. So this is the category of vector C. Okay, this is important for us. Now I introduce the notion of a functor very briefly. Okay, so this is the idea. You have two categories. C and D. Okay. The objects of C constitute the collection C0, and the morphisms constitute the collection C1. The objects of the category D constitute the collection D1 and D0, and the morphisms of the category D constitute the collection D1. And you have a map between these two categories, which we call a functor, in a compatible way. I'm going to explain the compatibility very roughly. Okay, so it is a good idea to see things in terms of diagrams. Say we have we have objects denoted by this x, y, z, and w, and the morphisms with f, g, h, and so on. We have a functor. This is the category C, and here we have a new category D, where x is morphed to fx, fy, fz, fw, so on and so forth. And the morphisms are under the action of this functor becomes f of f, this becomes f of g, this becomes f of h, and so on. Okay? So you see that in this particular case, the direction of the arrows is preserved. It may not be it may not get preserved in the way I presented. It may go in the opposite direction as well, depending on if it's a covariant functor or a contravariant functor. This is the case of the covariant functor or cofunctor. For present purpose, it's okay to explain, or it's okay to understand everything in terms of cofunctors. Okay? So let me take a break. I'll be back in a short while.